Good morning, good afternoon, or even good evening, and welcome to the fourth IEEE Low Earth Orbit Satellites and Systems workshop. Thank you all for joining this event, and we really appreciate your attendance from all over the world. My name is Budroweit, and together with my colleague Peng Hu, we will be the host of today's workshop on LEO ground station and ground station services. In collaboration with our chairs Markus Gadiel and Witold Kissner, and for sure the overall IEEE LEOSats team, we are very happy to provide you an exciting event with excellent speakers representing the different perspectives on satellite communication as seen from agency, commercial service provider, and optical link solutions for terabit data transmission. Today, we have 3 speakers for this workshop. Unfortunately, the 4th speaker got sick yesterday, and we were not able to find a suitable substitution. But I'm pretty sure that you will enjoy the 3 presentations today. In the first slot, we will have Marcin Gnat, my colleague of the DLR. He is with the DLR institution in Oberpfaffenhofen and is working on the GSOC, the Ground Space Operations Center. Our second speaker will be Eyal Trachtman from AddValue Technologies. And our third speaker is Yannik Horst with the ETH Zurich, talking about the optical terabit data transmission opportunities. This is the program for today. In total, we will have 3 presentations with roughly 26 minutes time slots. This program is planned on the minute and will be maintained throughout the whole workshop. Further organization about this workshop. So we encourage you to use the Q&A feature to ask your questions or post your comments. Selected question will be then forwarded towards the speakers by our moderators in the last 2 to 3 minutes for each talk. There's also a short wrap-up session at the end of the workshop to leave some room for additional questions and answers. This is a workshop, so your contribution and your input is really welcome. Every question will be saved in the end. They will not get lost, and after the workshop, the LEOSats team will post-process these one, and we will hopefully able to give you an answer afterwards. Talking a bit about the initiatives we are working in. So, to give you a global picture about the space sector. In the past, missions were usually driven by governments and agencies that usually covered military applications, Earth observation, or fundamental scientific missions. But specifically in the last decade, we can see that this has changed. We now have new players emerged, for instance, like SpaceX, Amazon, Virgin Galactic, or on the European side, new rocket manufacturers that are mainly driven by commercial interests. Examples for commercial interests are internet services, Earth observation missions, or general cheaper access to space. With the commercial drive, the new space era has begun, and we can see that this market is extremely growing and many new startups arises with new interesting approaches. This allows the development of new technologies and new applications which could potentially not be possible by the old and quite conservative approaches by agency-driven space missions. Access to space in the past was extremely expensive. An average price tag for a kilogram payload could easily get into thousands of dollars or even more. With commercial launch providers like SpaceX, for instance, we are now talking about thousands of dollars kilogram per payload. In the near future, maybe with the Starship platform, those value can be decreased to hundreds of dollars per kilogram payload. Low Earth orbit is not only attractive since it's faster and cheaper to be achieved. Another advantage of low Earth orbit is the shorter lifespan of the spacecraft. Shorter lifetime circles means less environmental stress to the systems. Thus, the systems may not be required to be built by full space qualified requirements, and the use of state-of-the-art technologies from the commercial off-the-shelf electronics may be suitable without taking too much risk. For sure, this is an extremely hot topic in the community, and how to handle the risk assessment for space mission while using commercial off-the-shelf parts in an environment that are not built for. But this is another topic, and maybe could be another workshop in the series of the LEO-SatS initiatives. But let's stay with reliability aspects for a minute. Another advantage on low Earth orbit is the cheap building of satellite constellations with primary required for global coverages, such as required for internet services. On the other hand, constellations allow new kind of redundancies on system level. If a satellite fails for some reason, it could be easily replaced by another one without having a loss of its desired service. Across with constellations, but not limited to them, standardization of satellite platforms becomes essential. It allows easier development and significantly reduces the manufacturing costs, since it's a certain point only the recurring cost plays an essential role. All the engineering work from the early phase of the design are probably not mandatory anymore. Same applies also for operation of satellites once a specific standard has been established. These activities are currently one of the most promising research activities in my personal opinion. So what is the opportunity about our initiatives from the technology and from the society point of view? You may not believe around 4 billion people on Earth still do not have high-speed internet access, and LEO satellites could change it. There is obviously a large economic drive. As an example, Elon Musk estimates that his Starlink constellation could bring in $30 to $50 billion per year once it's fully operational, even though building up this constellation would cost them more than $10 billion. Combining terrestrial networks and space segments can provide seamless global coverage with applications in Earth observation, communication, Internet of Things, and security navigation. The convergence of terrestrial and space communication systems also provides an opportunity for joint technology development, and the space sector in particular benefits from this economy of scale associated with dual-use components. There are many opportunities for advanced developments in various electronics, such as antennas, beamforming system, receivers, and transmitters, and network management and control software. There is also a demand on developing on-ground segments, like user terminals, gateways, to make the overall system viable. What's the vision of our initiative? The initiative aims to foster technical and educational activities in the LEO-SatS on a global scale. The scope of our activity is not to start a new space-related movement, but to coordinate and expand the existing activities with capabilities that could not be done without the help of the IEEE. Especially education is extremely important if we see the exponential growth in the space market. We want to attract high-quality universities and college students to IEEE through the collaboration with young and seasoned professionals to establish a network for their career. Even for the younger generation, we want to reach out to high school students and provide them with activities that we would not have otherwise. We need to make the space more attractive because this generation will be essential for our future. The evolution of space activities and the space companies really will rely on the right education. What we have done so far. So this is basically our third year as an initiative or as a project in general. And we have performed multiple workshops already. The last workshop was on AI technologies, and this workshop will be on ground stations. So we have fully transformed from the Future Direction Committee point of view into an initiative. We have grown in the past, we have established working groups, and we are looking for performing many technical activities at conferences and events such like that. And we're really looking forward to grow as a team. So if you're interested in joining us, please follow us on our social media channels like LinkedIn. Check out the website that we do have. You can scan the QR code on that slide, or subscribe the IEEE Collaborative to not miss any of our next activities. And with that, I would like to hand over to our first speaker, and I really wish you an enjoyable workshop. So our first speaker will be Marcin. Marcin, would you please be kind to start sharing your screen? A short introduction to Marcin. Marcin received his master's degree in electrical engineering in 2000 from the Technical University in Koszalin, Poland. Until 2010, he worked as a test engineer and in the semiconductor industry. Since 2010, he engaged at the space operation and astronautic training of the German Aerospace Center DLR, designing and managing the ground station network for various satellite missions like Grace Follow 1, Tandem X, EDRS, NMAP, Galileo, and furthermore. Beginning 2017, he took over the group lead of the ground operations since 2020. He's serving as a vice head of the Department of Communications and Ground Station. He is an active member and the Consultative Committee for Space Data Systems, so CCSDS, and the DLR representative at the Interagency Operation Advisory Group. With that, I would like to give you the floor.
Thank you very much. Yeah, I have today 20 minutes to go this topic, and I was considering what information in content would be fitting the best, and I think that what I'm going to present to you, and please don't pay so much attention to the presentation, but rather to the words which I'm saying, is trying to grasp an old world of ground stations and how this all currently touches onto the new space operations, operational concepts of the new satellites and new satellite missions. I will be talking today a little bit about institutional ground stations. So this is the area which I'm mostly firm into and what I know very good. And I know also their, let's say, advantages and disadvantages. I will talk about legacy communication aspects, so how to actually do this. I mean, the physics behind it is always the same, but the ways how we do it in, let's say, agencies is, yeah, to some people may be boring or old-fashioned, but of course this has some specific reasons. Then we have a typical cross-support constellations between agencies and commercial companies. Then I will drop a few words on exactly catching to the new space topics and how we can, let's say, accompany this. So we are not going, of course, to replace the whole commercial or segment on that, but we have to somehow cope with that. And finally, I will say a few words about standardizations. So as said before, or as Jan presented, that I'm also actively participating at CCSDS and IOAG. And these are the topics which are currently not so much present, I think, in the new space. I'm trying a little bit to bring it closer and to explain why maybe some standards are not so bad. And maybe you have been using standards not knowing that they are coming from these organizations. Yeah, so what are the institutional ground stations? Probably you see logos of some agencies known since many, many years. Started everything with, let's say, big communication stuff with Apollo program and so on. When people noticed, okay, you need some nice antennas and ground stations to communicate to astronauts. There is a movie known as The Dish, where in some Australian sheep farm, and a huge antenna or old radio telescope has to be used to support Apollo program. And so these are the things which are where we are actually coming from. So this time was the, so to say, the birth time of the communications as we know it actually today in the, let's say, agency related ground stations. How we operate the antennas, how they are constructed, how they are working. Of course, the devices, electronics, and everything has improved over the years, and we are having now solid state amplifiers and things like that. But in principle, a lot of these very legacy aspects of working and doing the communications to the space assets stayed the same. And maybe you should also keep in mind, it doesn't mean necessarily it's something bad when it stays the same. Yeah, of course, it's not as agile, and maybe it doesn't support fulfill all the requirements of the modern missions with thousands of CubeSats or something like that. But there is some reason for that. What you can see here, please don't try to read anything. So this is just to get an overview. This is a map which we created like around 2012, having placed all of our ground stations from the different agencies, which can be used for cross support. So it doesn't include, of course, any teleports and things like that, but still there was a pretty decent number. You can see also that they are congested in some specific places. So on that page, you can see some zoom in on that, showing east and west coast of USA, and of course in Europe relatively distributed. So we see already the one thing which is common to that is that ground stations mostly are located in some more urbanized locations. Yeah, so they need infrastructure, they need power, they need communications. And also from the historical point of view, this communication to the antennas, like the cable which was put in the ground, was not so easy as it is maybe today. Yeah, so this was the reason why the location of these antennas were like this. And the second aspect of locations of the ground stations were, of course, to get them possibly fitting to the mission requirements. And this is why also very remote locations happens. Like, for example, Svalbard, which you can see on the right top. This is also very early born, and there are several stations in Antarctica, and there are a few in the northern part of the globe. But generally, it stays also until today that it is very hard to put ground stations in these places. It's very expensive, it's expensive to operate it, and also the communication to these ground stations is hard still today even. Yeah, there are some other methods now to communicate, not only by fiber optics or just normal cables. We can use some Starlink terminals and so on to get that. And this is also moving a little bit into this direction to diversify connectivity on the ground to the antennas. So what is the typical characteristics of the ground stations from, let's say, legacy world, is that we have a very high level of reliability. Yeah, so these antennas are built to last and are built to work, and they have to work. Yeah, so there is no option like, hey, I maybe will work just 2/3 of my time, and the rest maybe it will be broken. So there is high level of redundancy in all of these components or components. Most of the antennas are completely redundant, except of course the main feed and let's say reflector part. But the rest of the electronics and reception and transfer electronics is completely redundantly set up. We have relatively large aperture size. We talk about typically what is from the older times still today 10 meters of diameter and larger. So the biggest antennas being at the moment around 70 meters diameter for deep space. And then of course there are some radio telescopes, which is a little bit different category of antennas. And this is also something which makes this whole thing very complex, because if you have such large a dish, you have to have mechanical stuff in the whole construction, which is keeping all that. You have to have engines which are driving the antenna, which have to be strong enough, and all this, it's like a domino effect. So at the moment when you start doing this, it goes one after another, and at some time point it is just very, very expensive. I'm not aware that the cost of building an antenna, let's say average antenna of that sizes, which we talk like 13, 15, 20 meters, that it dropped at any time. So it's always very large custom work. There are companies, of course, doing that, but there are not so many of them. And this all makes this very complex, the whole setup of the antenna. And of course, through all that, however, we are buying a very high flexibility. So we have a very high level of customization for the support which we perform. We can support plenty of frequencies, modulation schemes, coding, data formats, and so on and so on. So all this is configurable. It needs, of course, integration work, which takes sometimes a lot of time. This is something which one has to be clear about. So it's like you're buying something for something. So you get this high reliability. You can support human spaceflight missions with that, because it is not very likely that this antenna fails, and it can support different options. But then the high cost of operation is there, and it has a limited autonomy. So this is I thought that I will ask or talk about automation itself, but automation is not the autonomy. It's automation is like, can the antenna just drive based on some inputs from left to right and track the space, and this is what most of the antennas can do today. But autonomy is, what I mean is, when can antenna just be put completely on its own and nobody should care about it, just monitor from somewhere. And this is not the case in such of these antennas, not in that extent as probably a lot of people today would like to have it. So exactly because of the size, because of the mechanics, and because of the complexity of all of subsystems, this still needs some, let's say, human hand watching this and doing maintenances and so on. There's also a topic of optical ground stations. This is actually a stuff which I'm not going too much today into the details, but in principle, this is something which is exactly between new and old space. There's many years, of course, of experimenting on that, and this is now the times when optical ground stations are coming into the game. We are having still a little bit chicken and egg problem. We are building some ground stations and optical communications, but we have still problem verifying them, actually. So because there are not many missions actually performing direct to earth links with the laser. This is just a page very shortly, just to emphasize again this complexity of the typical, let's say, legacy agency like antenna. In the middle you have the diagram of the just standard diagram of antenna system, nothing special and nothing fancy. But all of these things which are around and how these boxes are actually implemented in case of our antennas, this is what it makes it on one hand exactly very reliable, but also very, very expensive. The best example is on the top. There is a cryogenic LNA, low noise amplifier, and it's not something which you are buying for probably very easily, and it's not something which you can operate for cheaply. But you can get 3 to 4 more decibels of your G/T from the antenna, and this is something which is very, very important for deep space missions. If you're receiving, for example, Voyager 2 spacecraft. So this is exactly what we are having inside. Now coming to the cross support, we have different agencies, and actually there are also commercial companies, some of them established already since many, many years, where they build kind of like small environment of people who know each other and support each other, because not everybody can have like antennas everywhere and doing everything. This is exactly because of these arguments which I said before, rather expensive, and very quickly the aspect of cross support came to the game, and asking the question how we can help each other. Important then is, of course, this WAN communication, terrestrial communications, mostly with some redundancy and based currently on MPLS technology. But again, what is coming with all of that is a relatively high cost and integration effort, because each individual antenna has to be integrated then in the overall network for a specific mission. Now, how we want to catch up a little bit, of course, there are mainly, one could say, many questions which are there. And I'm not going to go into detail anywhere to give you any answers to that, how the agencies or institutional providers are going to work with that. There are several solutions to that, and there are several approaches to that, better to say maybe. But how it will work out, the time will tell. In principle, the main problems are the cost. Yeah, so the driving antenna of agency of the size which I told you before, and tracking just as one CubeSat is just not really effective. Yeah, so it is very high cost on everything in comparison to that what you get. Then integration efforts, which I also mentioned, are pretty high, yeah, because exactly all is very highly customizable. But then even if you have very standard CubeSat and you want to use it, then you have to still do the configuration work even for that. So what we have to do, we have to learn to provide the support as needed and not as possible. Yeah? So we maybe also have to learn that not every pass for the satellite has to be 100% good, as it was always for many years, and for example for human spaceflight missions. We have to accept that maybe there will be some passes which will be wrong, because the overall service is important in the new space and not the individual, contact time of 10 minutes between satellite and specific antenna. So we maybe need some extension with some small antennas as well, which are cheaper, easier to operate, not so flexible, but exactly this. And we have to change the paradigms of planning and service provision. Yeah? So like we need to provide volumes of data or service in general and not delivering passes. Yeah? So this is something which now has to happen. It's still a little bit problematic. And there are still missions, especially the deep space ones and so on, where or the legacy missions, which exactly require this passes principle. And that's why this is a little bit always a balance, how to find it the best. And optical ground station, I already mentioned it before. This is just a table. I just wanted to include it in my presentation because I think this is very interesting for overall community to see the data frequency or frequencies, so to say, for communication. And this is from our CCSDS documentation or standards, a table. And you can see here that there is already, for example, a difference between near Earth communications and deep space communications. So there are some mismatch on the frequencies, which also, of course, has influence on the type of antennas you build and how do you equip them. But most important thing which I wanted to show you to here, that there is already some future communications. If you talk about optical as future, I mean, it is actually already there, but it's not really yet used at that extent as we probably would like to. And there is a V and W band, so very high frequency communication bands where you can get really thick gigabytes per second of data. And this is something which is going into this direction. And I think this will be especially important for the LEO satellites, because you can, decrease sizes of antennas and probably spend less power and have better and wider band communications. Now, at the end, last few minutes, very quickly, just mentioning exactly the standardization. So we have these two organizations. IEEE is a forum between agencies which tries to foster this cross support and also putting efforts on what things should be standardized, especially in communications, of course, which is important for cross support. And then these, so to say, guidelines are going into the CCSDS, which is, you can see on the left side, and there these standards are being produced. And one could always say, yeah, why I need these standards? It's all boring and so on. But if I took just these 3 examples here of blue books, so these are the standards of CCSDS, which probably many of you who are somehow connected to satellite operations or to some space business, you have been already probably confronted with. But maybe you didn't know that it is coming from CCSDS, but it is exactly the source of that. And there is some thoughts about how to do that. So first is, for example, telemetry space data link protocol, which is thus defining the format of the frame. So which bits and bytes what should mean to be capable to receive it from the satellite to the ground. The second one is radio frequency and modulation systems, so-called 401 book. So it's very popular, and it declares all of the possible communication ways, like at which frequency bands you should communicate to near space, which frequency bands you should communicate to the deep space, which modulation schemes you should use, what kind of ranging schemes you should use for deep space, for geostationary, for LEO satellites, and so on and so on. So all this is there standardized one page after another. And so it's very highly probably that if you are operating any satellite or doing anything with satellites, you are using one of these pages of this standard to do that. So even if you don't maybe explicitly know that the book number. And the last one is the orbit data messages, which is maybe a very general name, but in principle, these are the ephemeris information. And a lot of people think about TLE as being a standard for ephemeris, and it is kind of like industry standard, but it's not a de facto standard. And de facto standards for orbit projections or orbit information is exactly or are exactly defined in this book. And one of them is, for example, orbit ephemeris message, so-called OEM. And probably you have been hearing already about that, sorry, on that point. So, and the last page is just overview of all of things which CCSDS is doing. And I think that the most important is the bottom part, where you can see in which areas this standardization is taking place. And so I will go it through quickly. And you have, onboard services, so like onboard wireless standardization, application support. Then we have space link services. So these are exactly these telemetry or telecommand formats, 401 radio frequency modulation things, optical coding and modulation. Yeah, so all of these things which are happening on the physical channel are being standardized here. Then we have some cross support, so how to communicate between antenna and control center. And then there are onboard services like or interconnecting services like voice, file transfer services, motion imagery, or video in other way of say, or delay tolerant networking. And finally, ending up with all of the, let's say, management services and mission operation services, which typical control center needs, so to say, to operate their satellite the best. Yeah, so with that, I think I'm pretty finished. And I will be happy if you would have any questions. And yeah, thank you very much.
Thank you, Marcin. Indeed, we received a couple of questions, and I think we have a bit of time to give them to you.
Yep.
Let me just check. There was some questions riding in a similar direction. One of them is very interesting to me as well, as I do have my background also on RF systems. Do you think that it is possible that we can in future replace these large dish antennas with beamforming technologies?
Yes, but it's still, so to say, I will bring the map back. I think this is the nice thing to look at. I think yes. However, it still needs to be a little bit, let's say, experimented. How far we can get the data processing so good that we can get the similar or same result as if you would build just one single huge dish. Yeah, because alone from the physics it won't work. Yeah, I mean the principle, of course, array and so on is working, but the performance we can't get as close as if we build 70-meter dish. Yeah. But on the other hand, and this is something which learns also the story of coding schemes. if you previously, like, I don't know, 100 years ago, sent some signal over the radio, then it was dampened, and then you had a lot of errors inside. Yeah, and one could say also, physics is at some time destructive, and it just won't work. Yeah, what people came up with is just mathematics, yeah, and the coding, and all these data information theories and so on, and learned how to cope with that to get still useful data out of very, very, very weak signal. And I think something in that direction, like reconstruction of very, very weak data out of such arrays in some smart way may need to be, or maybe needed to reach similar performance levels. But of course, one thing which is very important, of course, if we take into account some atmospheric effects, this is something where huge antenna or huge subreflector or reflector is still advantageous in comparison to a smaller one. Yeah,
I agree with that. I see it personally, at least on the space segment, that people are really willing to use more beamforming technologies for sure. If they don't have the capabilities to install large dishes, even with that kind of new ideas of unfolding dish technologies in the space segment. But yeah, since we are moving really into higher frequency bands, you have mentioned it already, we are talking now about EW band, so about 300, let's say above 100 gigahertz. Then let's say from the physical point of view, the antenna is getting smaller, and then beamforming technologies could be also quite interesting. But yeah, there are clearly some benefits on using dishes at the ground station for sure. Another one is also quite interesting. You haven't talked about that in specifically because this is a really technical question. I know personally that, let's say, from the modulation schemes and stuff, that at least at lower frequency, let's say very simple technologies or modulation schemes are used. But do you see that somehow, let's say DVB-SX or DVB-S2 are standards that could be established as well for SATCOM? From the agency point of view, for sure.
Yeah, so I'm not aware of any experiments in this direction. Yeah, but from that, what I know, and I'm not expert in DVB standards. Yeah, by the way, they're also part of CCSDS. but yeah, I had to focus on something, and I always left it out a little bit. But from what I know, they're having a lot of this aspect of flexibility, exactly on variable coding modulations and things like that. And actually, there are standards for variable coding in modulations, which are, let's say, not necessarily DVB connected, but they use also all our normal comms standards and comms modulation schemes and so on. So there is a variable coding and modulation and adaptive coding and modulation standards, which allow exactly more flexible way of doing this, and actually more or less for A band and everything above, there will be almost obligatory if you want to get some senseful data from your LEO satellite, which is like flying over the horizon, and the slant range changing from 3,000 kilometers to 400 kilometers, and then again to 3,000 kilometers, and you can imagine that the change in the data rates due to some atmospheric effects can be huge, and for that one has to do this adaptive way of working to get the maximum. Yeah. So this is something which is definitely happening, I think, and there is a work on this direction. Yeah. Optical is, by the way, very similar in this respect. But I think what will be more important is, and it is also, as I think, especially with these constellations getting more and more clear, is not focusing so much on this individual pass, yeah, but rather to getting this overall service. Yeah? I want the data from the space to the ground. How it happens as a customer, or mission operator, people will start to say, I don't care. You as a ground station or communication provider in total has to solve it. Yeah, and then this solution can be, you can have two fantastic K-band antennas and try to grasp all of the single bits out of them, or you create 20 smaller K-band antennas which are not so fancy, but due to alone the coverage, you get so much data from the satellite that you can at the end provide to the customer their daily volume. Yeah? And with optical, it's even obligatory. So we know already that optical ground stations almost will be not making any sense just to make a single flyover pass. Yeah? So you can do it for fun, but not really operationally for longer term to get really amounts of data. This is just the weather is too unstable. Maybe there are a few places in the earth where you can always say, yeah, tomorrow it will work. But except that, you are really going to do this more like cloud approach to this communication.
Yeah. According opticals, we will have a dedicated presentation on that, so it would be interesting to see the other side. We have received many more questions, but I would like to hand over to our next speakers. Again, your questions are not lost. We will share these kind of questions to the speakers. And with that, I would like to thank you once again, Marcin, for your presentation. Thank you so much.
Thanks.
And Peng will take over with the introduction of our next speaker, Eyal Trachtman. And Eyal, in the meantime, you can already start sharing your screen, please.
Thank you. Bye.
Hey. Thank you, Jan, and thank you, Marcin. And let's welcome our next speaker, Eyal Trachtman. And I would like to briefly introduce Eyal here. Eyal received the BSc in Electronics Engineering and MSc in Telecommunications from Tel Aviv University, Israel. His technical expertise covers various disciplines in the field of mobile satellite systems, including modulation and coding, source coding, satellite multiple access, wireless packet, and networking. He holds 10 patents in the field of telecommunications and worked at Inmarsat UK for 23 years, and was leading the research and development activities at Inmarsat as Director of R&D, with a wide involvement in collaborative and strategic initiatives. He is the VP responsible for the business development and the service introduction of AddValue's inter-satellite data relay systems. He is focusing on business and technology strategies and leading and delivering collaborative and innovation programs such as AddValue's IDRS. So his presentation title is IDRS, a persistent always-on connectivity for LEO satellites. Over to you, Eyal.
Thank you, Pengu. And good morning, good afternoon, maybe good night for some of you who are listening to this workshop all over the world. So, Inter-Satellite Data Relay Service was developed by Inmarsat, now part of the Viasat, and also the AddValue Technology Singapore SATCOM specialist, with the goal of offering low Earth orbit satellites and operators and always on persistent connectivity between the LEO satellite and the ground. The IDRS service offers customers a real-time, on-demand, and always available full duplex IP data connection between the LEO satellite and the operation center on the ground, with an end-to-end network latency of less than 1.5 seconds. So with that, I'll start with the challenge of achieving real-time connectivity to LEO satellites. LEO satellites normally operate with ground stations where they have passes which last about 10 to 15 minutes, and then there is a period of latency until the next pass. So everything needs to be scheduled and concentrated into this pass, because there is no other way to connect to the LEO satellite outside of the passes. So that's where IDRS comes in and provides a solution. And time delay between connectivity intervals is an operational issue. and especially for time-sensitive tasking missions and responding to satellite anomalies. I can think about surveillance application, maybe alert messages applications, which need immediate access to connectivity to the ground. And that is simply not possible with ground station networks. Of course, the ground station networks have an essential role to play in terms of providing the ability to download data, payload data, at high volume of data at the time when there is a pass over a ground station. And that is true for radio ground station, in the future also for optical ground stations. But in terms of managing constellation, large constellation, and new space is really moving towards a large constellation of satellites, the real-time communication via IDRS or other data relays that might use the same technique is something which is essential for managing large constellations efficiently and in a streamlined way, rather than in a very constrained ground station limitation. So, on the left-hand side, you see the mode of operation for a traditional ground station operation, when there is a pass of a ground station every 45 minutes or 1.5 hours, or maybe even more time, depending on the orbit. And between these intervals, there is a large time where the LEO satellite is not connected. In contrast with IDRS, IDRS always looks up as a data relay service to a constellation of GEO satellites operated by Viasat. And at any given time, the satellite can see at least one of these GEO satellites in the upper hemisphere of the locality of that satellite. So Viasat provides global coverage at L-band with a constellation of GEO satellites, which include the Inmarsat 4 constellation, complemented by AlphaSat and complemented by the Inmarsat 6 constellation. So together, these provide a complete global coverage for a LEO satellite as it goes along its orbit. On the ground side, the system builds on the global connectivity, which is offered by the Viasat ground network, which is called BIGA. This network is composed of a few ground stations and an interconnect a private data network which connect to anywhere on the globe. So this is a system overview of how IDRS works. So you see at the top ellipse, you see the GEO satellite constellation at L-band that I was talking about. The customers, the LEO customers, are sitting at LEO orbits in the represented by the mid ellipse in this slide. And the ground network is represented at the bottom of the ellipse. It composed, as I said, with 3 major ground stations, which are called satellite access stations. One is in Pomolu in Hawaii, one in Fucino, Italy, and the last one is in Borum in the Netherlands. All these ground stations are connected with the data connection network, which is a private data connection network. On that network, there is the network operation center, the satellite control center, and also a range of point of presence in different major cities around the globe, where customers can connect via VPN to that private data connection network. So the end-to-end link between the LEO satellite and the ground operate via a service link of 200 kilobit per second full duplex. And then from there, it goes down to the ground via feeder link to one of the ground stations. And from these ground stations, the link continues to the points of presence and to the VPN, which connects to the terrestrial node on the ground. All that connectivity is done at IP. So each of our terminals, which sit on each of the LEO satellites, is actually an IP router with a static IP address. So from the ground, the network operations center can actually ping or connect to any of these static IP addresses in space at any given time, as long as these LEO satellites see one of the GEO satellites in their field of view. So here is a service coverage for 500-kilometer LEO satellite. You can see that the coverage is quite dense. What you see here is 5 satellites. So these are the Inmarsat 4 constellation plus the AlphaSat, which is part of the Inmarsat constellation, and the Inmarsat 6 GEO constellation. When we move to 600 kilometers, it's still very almost complete coverage as well. There are some gaps which you can see starting to open up in the polar regions, but predominantly the most of the orbit is covered, and of course it depends on the inclination of the LEO orbit. If you talk about sun-synchronous orbit, these orbits will reach the polar region and will suffer some lack of coverage. But for example, mid-inclination orbit or equatorial orbit LEO satellites would be fully covered, even up to 700 kilometers, which is this slide. In this slide, you see that the polar regions are now not covered. So when a sun-synchronous orbit satellite would go along the orbit here, it would be covered probably 85% of the time. And around the poles, there would be gaps of about maybe 10 to 15% of the time. So what are the IDRS connection characteristics? We talked a little bit about it already. So it provides provides always-on connectivity. It continuously provides connection to the LEO satellite. That connectivity is an inherent or intrinsic part of the system. It's part of the solution, and the customer does not pay for that connectivity. What the customer would pay is the data volume that is used. So we offer customers a data plan, very similar to a cellular operator, a monthly subscription for a data plan for so many gigabytes. And this is basically respond to the customer need for volume of data. And we even have family plans for constellations which basically combine all the constellation in one contract, if you like, and provide a solution based on the customer can actually use that volume of data any way he needs among the satellites in the constellations. I mentioned that we work on an IP at IP level, so we provide IP session continuity during the footprint of the GEO satellite, and it covers seamlessly the handovers between the geo spot beams on the footprint. So as long as the customer is within the footprint of the geo satellite, it would be connected seamlessly and with no interruptions. There is a short interruption when the LEO satellite moves from one geo footprint to the next geo footprint, and that takes about 20 seconds. And then the connectivity continues without interruptions. Latency is between 0.5 and 1.5 seconds end to end. The whole network, the whole link end to end is secure. The air interface between the LEO satellite and the ground is covered by a 3GPP protocol, which was developed by Viasat. And then on the ground, it goes to a private ground network. And when it reaches the point of presence, it would go to a VPN. So at any given time along this end-to-end link, there would be a very secure link available to the customer. The system is highly reliable and highly available, and it is on the network side, on the ground network side, is based on the hot swap between ground stations. Every ground station has a standby and active nodes, and if there is any anomaly on the ground, there would be a handover, a seamless handover between the standby and the active part of the network, what we call hot swap. So there would be no loss of integrity or no loss of availability for the customer. In terms of applications, the first one which I talked about at the beginning of my talk is the real-time TT&C and management of anomalies in real time. And this really offers customers the extension of lifetime for the satellite, because if you are able to, as an operator, to respond to anomaly in real time and not wait for an hour and a half or 45 minutes until you identify it, because you don't see your satellite until you go over a ground station, that these 45 minutes can be the difference between the ability to save the satellite or lose it. I also talked about real-time tasking. This is very important for surveillance applications or surveillance missions. And the ability to reduce the time between order and delivery of the data, whether it would be a hyperspectral or optical image or SAR image, we see more and more the demand for a reduced time between order and delivery. And we can provide this with real-time tasking. Real-time delivery of mission data and alert messages to the ground. So there are many missions that focus on alert messages. For example, identifying fire from space, or if you look into space missions, looking outside or into space, identifying in real time the start of a supernova event. All these events are very time sensitive and need immediate alert to the ground when some such event is being detected. So real-time and always available connectivity to the ground would be very useful in these cases, and IDRS actually provide that capability. Other applications that I might mention here are applications that that are time sensitive and they are low volume but high value data. And in this kind of application, we can count 5G, the NB-IoT, weather nowcasting, situational awareness, and awareness data like AIS or VDES or ADSB. And maybe more exotic, the TIP and Q missions and formation flying satellites, because as an IP-based service, we can actually connect between flying space platforms or flying satellites information and provide information from one satellite to the other without intervention from the ground. So I'm now going to talk a little bit about use cases and examples from our current customers. The first one is Capella Space. Capella is a SAR satellite constellation company, and with very high resolution imaging. We started to serve Capella Space in 2020, and there have been, to date, 12 operational satellites have been launched. And the lesson learned from Capella, what we hear from Capella is they need the always-on connectivity for managing the constellation, for the TT&C and tasking, but also for recovering from anomaly, which actually saved a couple of the satellites from early retirement. So that's Capella. I'm continuing to Synspective, which is another satellite company, Japanese one. Their focus is on providing real-time and responsive response to disaster management and disaster resilience. So IDRS provide them with this optimized operational efficiency in providing this quick response to disaster resilience with disaster management. The functionality is the same. It's the use of always-on connectivity and the real-time tasking, but the focus is slightly different. Our next example is another SAR, Japanese SAR satellite, IQPS. They are planning to deploy 36 SAR satellites in space, and the main focus there is to provide minimum interval between revisit times at any point above Earth. The use case will be exactly very similar to Capella and Synspective. Next example is Loft Orbital. Loft Orbital is a hosted payload satellite operator, and they would like to use IDRS to provide real-time capability to their customers for whatever missions they need. And really, it opens up the flexibility for customers, payload customers, to use it as they see fit. Our next example is Astroscale. Astroscale is an end-of-life service company. They basically capture satellites at end of life and retire them or deorbit them into a decaying orbit. They need IDRS because they need the real-time connectivity during the proximity maneuvering and capture of the client satellite when it's during the maneuvering to capture it. And last but not least, Atomos. Atomos is an OTV kind of mission. And again, they also rely on IDRS to do the rendezvous and the proximity operation while they have real-time control over the satellite. So that basically that's the conclusion of the overview. I would like to just, I see I have about a minute or two. I would like to show you our terminal, which sits on board the LEO satellite. So this is the transceiver that would sit on the LEO satellite. We have two options for antenna solutions. The first one is a directional antenna, in which the antenna is installed on the LEO satellite, and the satellite itself use attitude maneuvering to point the satellite toward the GEO orbit. So that complicates a little bit the operation. The CONOPS are slightly more complicated because the satellite operator would need to move between pointing the IDRS antenna to doing other tasks during the mission. So our other solution is a hemispherical antenna solution. That solution has 7 single patch antennas, which together create a hemispherical coverage. So each of these antennas covers a segment of a hemisphere, but together they provide the full hemispherical coverage, and therefore they provide autonomy to the LEO satellite operator, who doesn't need to assist IDRS in pointing toward the GEO. So that simplifies the concept of operation for the operator. With that, I'll finish, and I'll be happy to answer any questions.
Thank you very much, Eyal, for this nice presentation. We have received a couple of questions, and I would like to pick out one or two. These are a bit more technical related. So one of them would be, for instance, what satellite spectrum do EDRS use between geostationary and LEO? I mean, you have specified the data link in terms of 200 kilobits per second. So this may be a very low frequency band that's being used.
Yes, I might have mentioned it. It was actually on the slide. It's actually we operate at L-band. No, unfortunately, it's not on the slide, but all the Inmarsat I4 and I6 and AlphaSat satellite are all L-band based satellite. They operate at the mobile satellite service band, which is 1600 megahertz and 1500 megahertz in transmit and receive, respectively.
I see. Yeah. Another question more related to the ground segment then. So if you are a customer, what kind of ground station? Okay, this question has been answered already because you mentioned that you have these kind of ground stations distributed around across the world, and you as an end user just have access to those by the internet.
Exactly.
But maybe,
as a customer,
yeah, go ahead.
So as a customer, you have an IP address of your LEO satellite. That's all you need. You just send and receive IP packets from your headquarters, from your operation center to the LEO satellite, and the LEO satellite will send IP packets back to you. And there is no, you don't have to interface as a customer with the ground station. The ground station is completely transparent to the customer. From that perspective,
I'm just
it's a complete end-to-end solution.
Yeah, I'm curious. Are there only really 3 ground stations being used by Inmarsat that you have depicted in this slide, or are these kind of ground stations exclusively used by IDRS?
These are the ground stations that are used by IDRS. Inmarsat provides has other ground stations. I think one in Perth, And they have also ground stations, national ground stations, one in China, one in Russia. But for the purpose of IDRS and to connect to all GEO satellites, it's sufficient to use the 3 ground stations that we're using.
Mm-hmm. And are you expecting maybe with a new fleet of Inmarsat that this kind of bandwidth limitation right now can be improved? Because I mean, many people are really targeting to higher frequency bands and more bandwidth, more transfer capabilities, so that the only connection to your satellite with 200 kilobits per second may be not sufficient enough.
You're right. Our service is very complementary to the ground station, the network ground stations. Of course, we are limited in terms of bandwidth to the 200 kilobit per second in both directions. We cannot you cannot use IDRS for download of the big payload data. And for that, the customer would need to wait until it passes above a ground station to download the data. But with the advent of the onboard processing and edge processing and the increase in capability and capacity of software-defined radio, it is today possible to do a lot of the processing of the images or capture data on the LEOs and create products, low data rate products to download to the ground directly to the users. And many of we see this kind of trend progressing with many of our customers.
I see. All right, perfect. Once again, the questions that you have sent to us are not lost. We will forward them to the individual presenters afterwards. And thank you again, Eyal, for your presentation. And since our last, let's say, topic was about data throughput, we are moving on to our next speaker, which will be Yannik Horst. And now we are really entering the terabits per second data transmission by using optical solutions. And yeah, I would say Peng will give a short introduction about Yannik, and then Yannik can start sharing the screen and moving on with the presentation.
Yes, so let's welcome our next speaker, Yannik Horst. Yannik Horst received the BSc degree and MSc degree in electrical engineering and information technology from ETH Zurich, Switzerland in 2016 and 2019 respectively. He is currently working towards the PhD degree in a group of Professor Jörg Luthholt. His research interests include optical communication, microwave photonics, and plasmonic devices and their combination with high data rate, transparent radio over fiber links. Within the European Union project, Vertigo, he assesses and implements advanced modulation formats for high throughput optical feeder links. Over to you. Thank you, Yannik, for the presentation.
Yeah, thank you again for the introduction. So my name is Yannik Horst. I'm in the group of Professor Luthholt, and today we have now a bit more like talk about higher data rates and maybe not more on the system side, but more going maybe a bit lower level or lower levels. How can we implement one link? And here we show you how we can use coherent modulation formats and free space optical communication links to achieve line rates in the order of 1 terabit per second in a 53 kilometer turbulent channel. So before I start, I would like also to thank all my co-authors, in particular our partners, Thales Alenia Space and Onera. So why do we need such applications? So if we take a look at the figure on the left, we can see that in network communication systems, fiber-based and wireless communications need to coexist. So we have two possibilities. Either we stay in the optical domain, or we convert our optical signal to a radio frequency signal and then later on back. And as already discussed before, radio frequency technologies, they have a high sensitivity, in particular on the due to electrical mixers and electrical amplifiers. Also, eye safety have never been a concern due to the very broad RF beams, and yet there's always the discussion about the limited and allocated frequencies, which is mostly licensed, and there's a trend in research towards higher frequencies, so sub-terahertz frequencies here in the order of 100 to 1000 gigahertz, which allows us inherently to use higher signal bandwidths. However, the performance of state-of-the-art terahertz sources and receivers is limited to a few tens of gigahertz in bandwidth. Also, output powers are nowadays limited to a few milliwatt, and the conversion from the optical to RF and back costs us around 40 dB in power. So we ask ourselves, what would be the advantage of using optical frequencies? So by shifting to even higher wireless carrier frequencies, optical feeder links are seen as a way to overcome the RF bottleneck, and we can achieve very high throughputs, especially by using wavelength division multiplexing to make use of this vast license-free optical bandwidth. So, for example, C-band itself has around 4,300 gigahertz of bandwidth, and there are studies that with this high bandwidth, the number of optical ground stations can be drastically reduced in order to achieve high feeder link capacities. Also, the let's say inherent low divergence of an optical beam makes it in a point-to-point scenario not only secure against undetected eavesdropping, but also we can overcome very high distances in the order of thousands of kilometers. And then the maturity of photonic technologies does not only reduce the developing costs, but also photonic applications themselves, they're seen as a very size, weight, and power efficient technology. However, talking now about the big challenges are the weather conditions and the atmospheric turbulences, which I will discuss in the next slide, because they can highly attenuate and distort our laser beam. So we have here a table comparing free space optical communications versus radio over fiber links, and for different weather conditions. And we can see that radio over fiber links, they show a much higher robustness towards visibility limiting weather conditions. So pollution, fog, or snow, in particular fog and clouds, lead to very high losses. And there was an experiment conducted in Denver where we can see that for different, let's say, weather or fog conditions with different varying visibilities, so in general, we can say that the near-infrared light has more or less the same properties as visible light. So with a decreasing visibility, also the attenuation highly increases, and therefore data communication will not be possible. But again, if we look at the table on the left, we see that there are still scenarios where free space optics could outperform radio over fiber links, the very clear weather conditions, and therefore studies have been done that the kind of an 8 to 10 ground station, which are embedded in a site diverse network, here, for example, placed around Europe, they could it could be used to avoid cloud blockages and almost or achieve a 99% link availability. Now coming to the other big challenge, the atmospheric turbulence. So if we have a transmitter and we send out our optical data beam, in the beginning can be described as a electromagnetic wave with a planar wavefront and a Gaussian beam distribution. However, going further through the free space channel, the time-varying thermal winds will lead to refractive index changes in the air particles, and as a consequence, it will the speed of light varies over the XY plane, and the phase front will be distorted of our electromagnetic wave. And this will lead then to interference, so amplitude and phases will either add up or cancel each other out. And finally, this will lead to a time-varying power fluctuations in our optical fiber if we couple later on back. So now coming to the state of the art of optical or free space optical communication links for satellite or space applications. So it has to be added that this is still a very unexplored domain. There only have been a few demonstrations. Namely, there was an inter-satellite communication link between a LEO and a GEO satellite in the frame of the Copernicus program, leading to up to 1.8 gigabits per second in 2015 over a distance of 36,000 kilometers. Or recently, NASA successfully demonstrated a LEO to ground link with distances of up to 930 kilometers, and they could downlink up to 1.4 terabyte in this 3-minute communication window. So, but what we see, what is still missing is GEO to and from ground communication link, and that's why the EU Vertigo project was initiated in 2019, and it's a 2020 Horizon project, and its ambition is actually to push the data rate of a single channel towards 1 terabit per second for GEO feeder links. And here for 3 milestones were kind of addressed or defined. So the first milestone is that we look into different advanced modulation formats and assess them and implement them to have a high spectral efficiency, but also maintaining a high receiver sensitivity. Then the second milestone is to find mitigation techniques against atmospheric turbulences. So here, namely, we have aperture diversity, adaptive optics, or as a third option, error correction coding and interleaving. And then, as we still will have a lot of free space losses, also very high power optical amplifiers, so with output powers of up to 50 watt were developed, and then techniques how to later on combine them to reach even powers of up to 100 watt. So now to show the feasibility of such ground to satellite links, we performed an auto demo in this project, and we see here in the figure on the top, we see an aerial view of the auto demonstration, and on the bottom we see the elevation profile. So the optical transmission link comprises 53.4 kilometers, and then with a total elevation of 2,800 meters. So this experiment was conducted in Switzerland, and the optical transmitter was situated at the East Ridge building on the top of the Jungfrau Joch glacier, and the receiver site was at the Zimmerwald Observatory, which is close to the city of Bern. So in general, the channel conditions in terms of atmospheric turbulence can be described as very challenging, because we have this very long, almost horizontal link, and especially high turbulence conditions in the mountainous areas in the lowland area. So here we also have a block diagram of the experimental setup. So we have an optical transmitter where we first generate our data and then encode it onto an optical carrier, and then after amplification, it is sent out into the far field by the satellite terminal. So here we have a picture of the satellite terminal, which was developed by Thales Alenia Space. So it comprises a 20 centimeter telescope, but we have to add that only a sub-aperture of 4.2 centimeters was used for the downlink transmission. And then afterwards, it transmits, the signal propagates through the turbulent channel and is received by the optical ground station, where we, in our case, used a 35 centimeter telescope together with an adaptive optic system. which will explain in a second how it works. So this adaptive optic system then mitigates the atmospheric turbulences, and we couple back to a fiber, and then after amplification in 2 low noise optical amplifiers, we go then into an optical coherent receiver, and then finally the signal is evaluated by digital signal processing. So how does this adaptive optics work? So I already showed you the problems of the atmospheric turbulences, and now we have when the distorted wavefront propagates into our optical ground station, we have a wavefront sensor who consists of an 8x8 subaperture camera, and it analyzes the incoming wavefront with its distortions, and then controls a deformable mirror, which constitutes of around 100 sub-mirrors, which individually can shift the phase in the XY plane of our phase front, and therefore correct it back to a planar wave. And then after this happens in a feedback loop, and then afterwards, if we have a planar wave, we have then again the optimal conditions for coupling back to a single mode fiber. So now what this sounds nice in theory. So let's see also what this means in terms of performance and how much power we can receive more with adaptive optics. So here I plot the received optical power, so the power back into the fiber as a function of time for the conditions either the adaptive optics was used in purple or pink versus the adaptive optics it was not used versus the adaptive optics was used in green. And we can see, first of all, that these characteristic power fadings due to the atmospheric turbulences the numbers can be much less reduced. Furthermore, also we could increase the average power by almost a factor of 500, and we can see that in comparison to black, where a real geo feeder link was simulated, we have a much or we are kind of in a worst case scenario. So in general, we can say, okay, adaptive optic helps a lot, but still the average powers we receive in the fiber are relatively low, on average around -26 dBm. And if we think again about our vision of having ground to satellite links, we want to overcome even higher distances, meaning also free space losses will quadratically increase with the distance, and low signal to noise ratios are frequent. And therefore, there's the need of a novel modulation formats. So we have a quest on improving the capacity and find out which modulation format performs best at lowest SNR conditions and can transmit the highest data rates. So here in the picture on the left, we see different modulation formats and their spectral efficiency as a function of required SNR to achieve a bit error ratio of for 10 of the power of -3. We have the Shannon capacity limit in black, and then also an auxiliary line, which is used to compare the modulation formats to our baseline modulation format for QAM or BPSK. So in general, what we are looking for is in comparison to our baseline format, we want to go to the left, which means we need a lower SNR to achieve the same bit error ratio. And at the same time, we want to stay more to the high spectral efficiency in order to send a lot of bits and don't use a lot of bandwidth. And recently, our group introduced a new modulation format, which works in the 4D space, so also uses polarization states to encode information in combination with constellation modulation, and we could show that it achieves a spectral efficiency of 0.8 bits per symbol and has a 1.7 dB advantage over QPSK at this bit error ratio. And we take now this new modulation format and put it into test versus also the QPSK and also a polarization QPSK, which is known also to have a very high sensitivity. And we fix now our line rates to 100 gigabit per second in our 53 kilometer link. And we can see as expected that we achieve this 1.4 dB or we could measure 1.4 dB advantage over QPSK versus 1.7 dB simulated. Then on the other hand, we have a reliable communication of 1 gigabit per second for received optical powers of down to minus 51.2 dBm, which is around 0.1 microwatt. And if we go then even to higher data rates, we were limited, or we could achieve data rates of up to 200 gigabits per second, which was limited more or less by the equipment we have, mostly by the 35 gigahertz dual pole IQ modulator, which we used here. So now, as we showed a higher sensitivity, as we had relatively high or received optical powers, we also went into the other direction. So what are the maximum achievable data rates we have in this link? And these are plotted here. So we have the line rate or the net rate as a function of symbol rate for higher order modulation formats. And we see the line rate in dashed and the calculated net rate for high received optical powers of around minus 20 dBm as a solid curve. And we can say, okay, we could achieve high symbol rates of up to 126 gigabaud for QPSK and 16 QAM. And by using high order modulation formats, we could even achieve line rates of 1 terabit per second by the use of 16 QAM and 64 QAM. And now if we compare the line rate and the calculated net rate, we see that 64 QAM performs better. And this was mainly due to the bandwidth limitations of our IQ modulator. So then we ask ourselves, okay, what would be the benefits if we don't have the bandwidth limitations of our equipment? And in this way, we now look into a different kind of modulator, which is called a plasmonic modulator. And in these plasmonic modulators, they showed a bandwidth of 100 gigahertz in a packaged module, and we put them in our link. And we also know that unpackaged plasmonic modulators have a bandwidth of up to 500 gigahertz. And this was only a Mach-10er modulator, so we now limited to sending real valued signals, so not complex modulated signals, and also it's a single polarization. So we test now our link for amplitude shift keying data modulation formats, and we look here now at the performance bit error ratio versus symbol rate, and we can see indeed we could achieve higher symbol rates by using a modulator with higher bandwidths as expected, and the highest symbol rate we could achieve was 160 gigabaud below this so-called soft decision forward error correction limit, and this results then into net rates of 176 gigabits per second. So in summary, we can say that we expect to achieve even higher data rates if we now have a dual pole IQ plasmonic modulator. So finally, talking also a bit about our ongoing activities. So we were, as I introduced also our Vertigo project, one of the milestones was to develop and test 100 watt optical amplifiers. This is mainly to overcome the very high free space losses, if we want to really go to space. And these are now currently tested with our partners in Paris from Thales. And here you can see the setup. So we have an optical transmitter. We split our signal into two parts. We amplify them, whereas each of these amplifiers can have output powers of up to 50 watt. And then the next step, we coherently combine them in free space. Then we also want to emulate the channel, the free space channel, by reducing the output power. And then finally, we couple back into a pre-amplified coherent receiver and look into the performance. So what we want to investigate are different modulation formats, different symbol rates, and also, of course, different received optical powers, and to see if nonlinearities of the high power optical amplifiers have an effect on the modulation format, and which modulation format can then again achieve the highest data rates as a function of input power. So this comes me to the end of my presentation. So what have I shown you today? So we showed you 53 kilometer links where we achieved up to 1 terabit per second line rates. We used advanced modulation formats to also achieve high sensitivity, and by sending 100 gigabits per second with received optical powers down to 0.1 microwatt. And finally, we have an adaptive optic system which could increase the received power in the optical fiber of a factor, or could increase the factor of the power in the fiber by 500. Lastly, I would like to also acknowledge the financial support of our Vertigo project and thank all our partners from Jungfrau Joch, the University of Bern, ESA, and SKW Logistics. Thank you very much for your attention. Are there any questions?
Thank you very much, Yannik, for your nice presentation. Indeed, there are some questions, some very technical related ones. One was about the measurements in terms of the different modulation schemes that you have performed. Did you make any kind of error vector magnitudes measurements on the QPSK for transmissions? I think there was a slide. I mean, you have shown these kind of nice bubbles, and coming with that, as a communication subsystem engineer, I know that the error vector magnitudes plays an essential role.
Yes, I mean we now here show them in bit error ratio because this I mean technically it's the most transparent let's say figure of merit, but of course I have to check our data, but we also have the error vector magnitude as a figure of merit. It depends what we want to kind of how we want to plot the, let's say the results, but everything is, I would say the bit error ratio and also the error vector magnitude is an indicator, or it depends on the signal to noise ratio. So it's just a different figure of merit we use, but we have to answer your question, we have the error vector magnitude information. It has to be also added. Yeah, so.
Go ahead.
No, it has to be added. So we use to have all these different modulation formats tested. So what we did use is we took like a lot of measurements and kind of assumed over these measurements the atmospheric turbulence is constant. So that's why we don't have like we don't have like clock synchronization problems. Of course, if the power in this, let's say, time slot we take the measurement is too low, then the measurement fails. But technically, this also gives us then the opportunity to plot the performance as a function of input power or received power at the ground station. Yeah.
Mm-hmm. You were mentioning that the bit error rate desired or required was 10 to the power of -4. Where is it derived from? Do you know that?
Yeah. So I mean, technically, I think there are lots of bit error ratio thresholds coming. Then I mean, we're not experts in forward error correction coding, but if we talk about information rate and mutual information, then mostly the bit error ratio for 10 to the power of -3 is considered to be like that let's say the coding overhead is so small that let's say the line rate, so the data you send and the data you receive is more or less the overhead is almost zero you need for forward error correction coding. But it can be discussed. I mean, there's different implementations possible. Also, others talk about okay, 10 to the power of -9, but yeah.
And regarding this slide, there was a question compared to the performance of different modulation orders. What kind of waveform are used in the results?
You mean pulse in terms of pulse shaping?
No, the exact question was you compared the performance of different modulation orders.
Yeah.
And the question is waveform used in the results. What kind of waveform has been used?
Okay. I mean, so for example, this, I'm not sure if I understand the question, but more, I mean, waveform, so there's either the way understanding waveform as a kind of the pulse shaping. So this would be square root raised cosine. And then the waveform could be also interpreted as the symbol rates we used. And then here, for example, we have different spectral efficiencies as shown in this graph for each modulation format. So we put more or less the bandwidth for each modulation format, so we achieve the same line rate. So this line rate divided by the spectral efficiency gives us then the bandwidth or the symbol rate needed.
Okay,
but I'm not sure if I understood the question correctly. Maybe
for me the same. Maybe if the question was answered in the right direction, the people can respond to this. Otherwise, they can specify the questions in a more detailed way.
sure.
Anyhow, I may have a last question. The setup that you have shown in one of these pictures. I mean, it's still an early phase investigation for sure, but on a pragmatic way, do you see that these kind of technologies can be used in also smaller satellites, which could be suitable for LEO, or is it really just for large satellites in terms of geostationary big ones? Or do you see that these kind of technologies would be also suitable for LEO missions with smaller sizes?
It's a good question. I mean, we always in the project try to, first of all, of course, the adaptive optics system is only for ground stations because of place, power consumption, and so on. Regarding the, let's say, the transmitter itself, because this now, or if we look at the link, in this case, it's a downlink. So we, I would say, I mean, what we always investigated is, okay, we have output powers for the satellite terminal of around 10 watt. So I'm not sure if this is also considered for LEO satellites, but in terms of equipment we used or we intended to use also, I mean, we started, for example, looking into the plasmonic modulator if it's a kind of qualifies for space because it's kind of a very low footprint modulator. But yet, I would say it's more what we did here is a proof of concept to that line or that we can achieve a really high data rates, but also the equipment we used is not space qualified and was like more like I don't think that we use, for example, arbitrary waveform generator, which has over 100 giga samples per second. So I don't think this is also intended in the near future to be space qualified in terms of costs. But what we see is that coherent modulation itself, it goes very into the like interest independent of the LEO or GEO satellite to be kind of, or in general, coherent modulation schemes and reception.
Yeah. Excellent.
So,
perfect. Then I would like to thank you once again for the presentation and the nice insight of your recent studies. Really looking forward how optical solutions can improve the SATCOMs, not only for LEO, but in general. For sure, we have seen that there are some constraints with optical links, and there's a nice controversial discussion between RF and optics. But that's a different story, I would say. Yeah, this brings us actually already to the end of this workshop. It was very nice to have you all on board and having these nice discussions and this nice kind of presentations. Also, thank you very much for all the attendees staying that long. I was really hoping that we had this 4 speakers because one of you or a couple of you already mentioned that the insight of the academia perspective of you is missing, and for sure with amateur radio bands and with certain distributed networks on ground stations for the university approaches is kind of interesting and challenging as well. And I hope that we can maybe get the presentations afterwards as a recording that we can then distribute it throughout the overall recordings for this workshop. This will be published at IEEE TV in a couple of weeks, I hope so. But yeah, thank you once again to all the speakers, to all the attendees, to all the people in the team organizing this workshop. And we are really looking forward to see you next time with our next workshop. And stay tuned. Have a great day, have a good evening, and stay safe.